This is a second example here, how to apply the finite difference method for transient analysis. And this is the one-dimension bar exposed to Dirichlet boundary condition to the left, 100 degrees C, and on the right-hand side, I'm exposing the phase to a convection stream with T infinity equal 20 and the convection heat transfer coefficient of 10. Alpha is given, delta X is given, and the total length is also given by 0.6 meter, and delta X is 0.6 meter. So now I would like to repeat and get the temperature distribution at time equal 1 minute, 2 minutes, and 6 minutes. So if you recall the previous example, we did solve the same problem with the same given information, but in that problem, we didn't apply that convection stream in here, but node 0 was set up at 20 degrees to have a pure Dirichlet boundary condition. Now, I'm adding that convection term to start integrating or involving the use of the energy balance method. And there's a second reason I'm solving that example as I discuss further. It's about the stability criteria that we talked about to select the time step to ensure getting convergence of your solution and getting realistic answers. Again, I look to the problem here. We know what's this is my design. I know what's my governing equation. It's partial 2t by partial x squared plus q dot over k, which is going to go away, equals 0. We don't have a heat generation here. This is going to be actually 1 over alpha partial t by partial time t. So that's my governing equation. I can discretize it. Then I will end up having the same equation that we developed. Ti p plus 1 is equal to Fourier's number Ti plus 1 p plus Ti minus 1 p plus 1 minus 2 Fourier's number multiplied by TIP. So this is for interior node explicit method, right? So this equation can be applied for any interior node. So I can apply this for node 1, 2, 3, 4, and 5, and we already did that. Before I move forward with that, we already picked up the item, and we were able to find delta t has to be less than or equal 5, and we decided to go with time step equal 2.5 seconds, and we went back and calculated Fourier's number for that value. I'm trying to recall, it's 0.25. So we were able to develop that, and we got these equations. So let me list these equations again for node 1 through 5, right? So we got the following equation for the explicit method. So for node, I will start backward. Node 5, we got T5 at P plus 1 equal to 0.25. T4 at P plus 1 plus 100 plus 0.5. T5 at, sorry, that's P. That's P. We are solving explicit, so that's P. Then for node number 4, T4 at the new time step is equal 0.25. T3 at P plus T2 at P plus 0.5. T4 at P. For node 3, you should have T3 P plus 1 equal 0.25. T1P, T2P plus 0.5, T3 P. For node number 2, T2 at the new time step equal 0.25, T1 plus T0, now it's an added unknown, plus 0.5 T2 at P. Now, oh, sorry, that should be 1 and 3, right? We are at node 2, so take 1 and 3. At node 3, take 2 and 4. We at node 4, we take 3 and 5, correct? Then at node 5, we're going to take 4 and 100. So at node 5, you take 4, 100, then the 5 itself. When you go for 4, you got to take 3 and 5 and 4 itself. At node 3, you got to take 2 and 4 and 3 itself, then 1 and 3 and 2 itself. Then node 1, the equation T1 at P plus 1 should equal to 0.25. T2 is one of them, plus T0 is the second one, plus 0.5 of T1 to the P. So these are the equation. No surprises here. We got very similar equation last time in the previous example. Now, what's going to be new for us is actually node 0. So let's see how we're going to develop the equation for node 0, which is exposed to a convection boundary condition. Let's see if this is going to be different than what we did before when we were solving like steady state, or it's going to be very similar. So I would like to apply the energy balance method for node number 0. I'm going to magnify a little bit that node. So that's node 0. I should have node 1 somewhere in here. 0. That's 1. Then my control element is halfway. So that's my delta X over 2. And let's see, there's no heat generation here. There is heat coming Q1. That's the conduction contribution. And I have here Q2 that's coming by convection. And remember, we are solving unsteady problem. So what's the energy balance equation? It's energy N plus energy generated, you can put the dot, equal to energy out plus energy stored. Energy out is 0. It's against the assumption of the energy balance method. There is no heat source, volumetric heat source, so E generated is out. So now I have En equal E stored. So En now is presented by Q1, which is a conduction, K, A, T1 minus T0 divided by the distance delta X. Q2 is a convection, it's HA. I have T infinity here, and the heat has to go into the element, so it's going to be T infinity minus T node. Up to this level, this is what we did when we solved steady state. Now, we have an extra term, how to calculate the energy stored term. Energy stored is equal to MC partial T by partial time T, and this is rho times the volume of the element, right? So this will be actually rho C. The volume of this element is A delta X over 2 times partial T by partial time T. So now let's collect the pieces together. I should have the following: K, A, T1 minus T node over delta X plus H, A, T infinity minus T node should equal to rho CP. We know that for solids, C and CP and CVD are the same. I'm going to call that CP to be consistent with the heat diffusion equation. Then I have A times delta X over 2. This gives me the volume of that control element, partial T by partial time T. A will goes away from all of them. Now I can multiply by delta X over K to free the terms here. So if you plane out the equation, you will end up having T1 minus T node plus H delta X over K times T infinity minus H delta X over K T node is equal to rho CP over K delta X squared over 2. Then you will have partial T by partial time T is going to be T node at P plus 1 minus T node at P divided by delta T. So now I discretize the first derivative of temperature to the time by the finite difference method. And again, this is going to be P, this is going to be P. What else? Now I can simplify K over rho CP is alpha. So this will be 1 over alpha. And I will have delta x squared and delta t. I know alpha delta t over delta x squared. That's Fourier's number. So the right-hand side will end to be 1 over 2 Fourier's number t node at p plus 1 minus t node at p. And now I'm going to take that h delta x over k. I look to the unit. It's watt per meter square Kelvin times meter divided by watt per meter Kelvin. You're going to get surprised that it's dimensionless number. We call that actually Biot number. And we give it the pi as a symbol. So I can rewrite this above equation here to be T1P minus T node P plus Biot number T infinity minus Biot number T node equal this term. Now we can actually bring, that's P. Actually, there is no P here. That's T infinity. That's P. Anything else that's missing? No, I don't think so. You can cross multiply that to Fourier number. I will have T1P plus Biot number T infinity. So 2 Fourier number, I picked up this term and this term. I will have here minus 2 Fourier's number, right? 1 plus Biot number, that's T node P. So it's minus 1 minus Biot number. So I take the minus outside, so it's going to be 1 plus Biot number. Then it's multiplied by 2 Fourier number from this side. This should equal be T node P plus 1 minus T node P. This term can go into this side as well. So I would have 2 Fourier's number T1P plus Biot number T infinity. Then I would have plus, let's keep that 1 plus, actually minus. That one is coming from this term, 2 Fourier's number minus 2 Fourier's Biot number. This is totally multiplied by T node P. This will give me T node P plus 1. So this is the final equation for node 1 at any advanced time step as a function of the previous time step data. So I can write it down as Ti at P plus 1 equal to 2 Fourier's number Ti at P, Ti minus 1 at P plus Biot number T infinity plus 1 minus 2 Fourier's number minus 2 Fourier's times Biot number times Ti to the P. And for the interior node, yeah, you remember that formula. It's Ti P plus 1 equal to Fourier's number Ti plus 1 P plus Ti minus 1 P plus 1 minus 2 Fourier's number times Ti P plus 1. So, sorry, that's just P. So this is the equation for the interior nodes. And this is the equation for the surface exposed to convection node. Okay, what's new now? Now, we used to take that term, we call it the stability criteria, and we were able to calculate the time step out of this equation. If you recall that, again, keep in mind, Fourier's number is alpha delta t over delta x squared. Now we have a new guest, which is Biot number. It's h delta x over k, right? So now from the second equation, the stability criteria said that Fourier's number has to be less than or equal half, right? Because 1 minus 2, Fourier's number has to be greater than or equal 0. So Fourier's number has to be lower than or equal half, less than or equal half. Fourier number is alpha delta t over delta x squared should be less than or equal half. So delta t can be calculated from delta x squared divided by 2 alpha. And this is what we did in the previous example. We know what's alpha 10 to the minus 3. Delta x is 0.1. I was able to calculate delta t to be less than or equal 5 seconds. But now I'm getting a different equation involved in the problem, which is this equation here. And there is a coefficient of the history of the node of interest, Ti, and this coefficient should not ever equal 0. So this 1 minus 2 Fourier's number minus 2 Fourier's number bio number should also be greater than or equal 0. Now let's isolate Fourier's number from here. So I would have 1 minus, take 2 Fourier's number as a common factor, it will be 1 plus bio number should be greater than or equal 0. From this equation, Fourier's number should be less than or equal 1 over 2, 1 plus bio number. And Fourier's number can be substituted by this term, so it's alpha delta t over delta x squared should be less than or equal 1 over 2, 1 plus bio number. From this, I get another equation for delta t that's equal to delta x squared divided by alpha, very close to this guy, and there's 2 alpha actually, so it's the same one here, but it's divided by 1 plus 1 bio number. Oh my gosh, this t has to be less than or equal this. So now I'm getting a different delta t calculation here. So if I follow that calculation, that's 0.5 squared divided by 2 times 10 to the third minus 3 times 1 plus, what's bio number? H is 20.1, H is 10, I'm sorry, and K is 10, so it's 0.1. From this, you will calculate a new delta t. It's not going to come to be 5 seconds. It will be actually 4.55 seconds. So what do we have here? We have 2 time steps. Each one is driven from different stability criteria. So how you choose your time step? You choose a time step that satisfies both stability criteria. So the first one is telling you that you have to pick up delta t less than 5. And the second one is telling you have to pick time step less than 4.5. So if you pick up delta t equal 4 seconds, that's satisfy both of them. So based on what we did in the previous example, delta t selected to be 2.5 seconds was more than satisfying both criteria here. So that value is working fine. I can use that value and proceed in my calculation. Now I can stack all the equations for all the nodes, right? So let's list all of them together here. First, let's actually calculate Fourier's number from this. It's alpha delta t over delta x squared. Since I'm picking delta t to be the same, so we'll get Fourier's number to be 0.25. In this case, the equations that was developed in the previous example for the interior node will be the same. It's not going to change, right? So let's write down the equation here. So for node number 5, or node number, yeah, let's do that. Node 5, the equation is actually, let's write it down. T5 P plus 1 is equal to 0.25 T4 P plus 100 plus 0.5 of T5 at the time P. Then for node 4, T4, the P plus 1 is equal 0.25 T4, T3 at node P plus T5 at node P plus 0.5 of node 4 at the current time step. For node 3, T3 at P plus 1 is equal 0.25 will be T2 and T4 plus 0.5 T3 at P. For node 2, T2 at P plus 1 should equal to 0.25. It would be 1 plus 3 plus 0.5 of T2 itself and everything is picked up at the previous time step. Now node 1, T1 will equal to 0.25. For node number 1, I'm going to take T0 and T2 plus 0.5 of the T1 itself, P, P, P. And now the new equation for us is node 0, and the final equation came to be T0 at P plus 1 should equal to, I will write down the equation first, 2 Fourier's number T1P plus bio number T infinity plus 1 minus 2 Fourier's number minus 2 Fourier's number bio number multiplied by T node at P. Again, we got Fourier's number is 0.25. We got bio number is 0.1. So let's go and substitute in this equation. So T node at P plus 1 is equal to 2 times 0.25. T1 at P plus 0.1. T infinity is 20 plus 1 minus 2 times 0.25 minus 2 times 0.25 times 0.1. And this is totally multiplied by T node P. So you'll have T node at P plus 1 is equal to, I think I did collect that node. It's going to be 0.5 T1P minus this will give me 2 plus this total term will be actually 0.45 T node to the P. So that's node 0 equation. So this is P as well. That's P plus 1. This P plus 1. So these are the equations. In addition to this equation, then these are explicit method. You start with your initial values. So you list your node T1, T node all the way to T5. Then at time equals 0, you guess everything to be 20 degrees. Then you substitute in the right-hand side. Then you take the data, calculate the data at time equal 0.25. You have the data values here, right? Then after you take the data values here, this is the data that you're going to use for the next time step, which is 0.5, and so on. Let me show you the numbers I'm getting for the calculation. These are the numbers I got after 60 seconds as the problem is asking for. At 60 seconds, I got, we're starting from T node, so I'm getting 32.1, 34.99. I got 41.61. I got 51.95. I got 65.71, 82.13. Now you move to 120 seconds. I got this to be 48.77. I got this to be 52.69. I got this to be 78.03. I got the next one to be 83.32. I got 88.78. That's 120. 48, 52, 78. Actually, I missed one. That should be 58.8. Then the next one is 66.94. Then I got, actually, let me list these data again. I apologize for that. At 120, it's 48.77. I got 52.69. then 58.77, 66.94, 76.87, 88.09. Okay, that's at 120. Then you try to do that at 360 seconds. That's what the problem is asking for. I got 68.02, 72.92. I got 78.02. Got 83.32. I got 88.78, and I got 94.35. Then you'll find yourself can reach a steady state about 800 seconds. And if you solve for 800 and 1000 seconds, you will get the same results that's near to the steady state solution. So again, this is just a second example showing that I think the outtake of that exercise here is how to integrate both the finite difference and the energy balance method. This is what we did for node number 0. And what's more important here is you may experience different stability criteria for calculating your time step. You have to be sure that the final time step that you pick is satisfying all the stability criteria, regardless of the type of the nodes. This is very important to consider to be able to get a correct answer, or to actually get a conversion and get a final solution into your iteration method. Otherwise, you may end up having oscillating solution. Values keep, so you see that values are going up all the time until you reach steady state. If your time step is not selected correctly, you may actually going up and down, or you are diverging away from the solution. So you could exceed the right solution, or you're actually decreasing the temperature, moving away from the right solution. So this is very important to consider. If you have multiple stability criteria, pick up the time step that satisfy both of them to ensure the convergence and the accuracy of the solution. So the next step logically would be actually the highest level of implementing the finite difference method is to have two-dimension problem with mixed boundary condition, with heat source internally, and unsteady problem. So that's going to be the ultimate situation you can experience, and it's going to be the most time-consuming problem to solve manually as well. But it's a good practice that's going to include everything up to now in utilization of finite difference method, regardless of the condition, regardless of the solution steady or unsteady. That's the best exercise you can do. See you guys with the next slide.